Okay, thank you. Well, there's a title of the paper. It is a pretty lousy title. Here's a somewhat better title, Correctness of Program Transformations in a Probabilistic Programming Language. So I'm going to repeat a little bit of what you've heard a couple of times today. What is a probabilistic programming language? Well, we think of a probabilistic programming language as an applied lambda calculus with two effects. There's an effect called sample, which is going to draw a sample from a source of randomness, and factor, which gives a weight to the current run. It gives a score. Why use a PPL? Well, we use a PPL to model a stochastic process and to infer values based on observations. What does that mean? Let's take a look at an example. Here is a simpler example than the one Adam just had. In fact, I had linear regression as my first example, and I ripped it out and replaced it with this one, which I hope will be a little simpler, if that's possible. So let's imagine that I am walking in the desert, and I know that I walk at about 5 kilometers per hour, and my actual walking speed is described by a normal distribution centered on 5 with a standard deviation of 2 kilometers. I also have a GPS tool, but it's not very good. It gives an unbiased result, but the standard deviation is 1. So I walk for an hour, and I send back a measurement from my GPS saying that I have gone 7 kilometers. We do assume that I'm walking in a straight line. I walk for another hour, at which point the helicopter is supposed to come and pick me up. Where should that helicopter go? Where am I likely to be? Well, we can model this situation in our PPL. So here we have my distance after 1 hour, which is described by a normal distribution with a mean of 5 and standard deviation of 2. And by the way, there is an occurrence of sample hidden under that normal there. And if you look at the distribution, there's the distribution of my position after an hour. Now we observe the GPS. So the GPS says, you appear to be at 7. The standard deviation is 1. Right? So now we have 2 sources of information about my location. My prior, based on what I know about my walking speed, and what my GPS says. Right? I think I'm at 5. The GPS thinks I'm at 7. How do we weight those? Well, the obvious thing to do is to multiply them. That's what the factor is for. Right? So if we multiply, we get the purple curve, which in fact shows the peak, well, right around 6.5 according to that picture. Now, of course, that is not a probability distribution because we just multiplied 2 probability distributions, so we get something smaller. So we can normalize that to get the probability distribution, a distribution that shows the probability of my position after 2 hours. After 1 hour. Where am I after 2 hours? Well, my distance after 2 hours is where I was after 1 plus another hour's worth of walking, which is 5 with a standard deviation of 2. And to combine those, it turns out that the right thing to do is not to normalize, but to just consider these things. These unnormalized probabilities are called measures. And you combine them, and those are the measures that you get. And then you can normalize them again, and hopefully the helicopter pilot can do this, and he will come pick me up in the place where I am most likely to be. Now, if we want to implement this, there are lots of things we could do. We could draw randomly, draw random samples, but as Adam points out, that's pretty inefficient. Question is, are there transformations? Are there things we can do? Are there things about the algebraic structure of these distributions that we can take advantage of in order to improve the performance of our algorithm, get the helicopter there faster? Well, the first thing that strikes me at least is that all these curves are the same shape. They're all nice Gaussian normal curves. Can we take advantage of that to compute the answers more efficiently? Could we move that currents of that factor statement around? Are there other transformations that might be useful? And of course the answer is yes, otherwise I wouldn't be here. There are a bunch of different kinds of transformations. There are transformations that are based on mathematics. For example, if I take my program run, my program sample, and I factor it by x, and then I factor it again by y, that's the same as factoring it by x times y. There are a bunch of other transformations having to do with the algebraic properties of the Gaussian distribution under translation here. Okay, there are more transformations based on what's called conjugate families of distributions, which are families of distributions that are closed under product. And the folks who write these models know that they should be writing their models in terms of these conjugate families, because that allows lots and lots of good optimizations and good transformations. So there are lots of transformations of that form. Now here's a really interesting and odd transformation. Here's a program. I draw some of my randomness, and I compute a value x. I draw some more randomness and compute a value y, and then return some f of x and y. Conversely, the other thing I could do is take the first bits of my randomness and compute y, and then take the next bits of my randomness and compute x. Now, these programs are unlikely to be equivalent in any language that has effects. Right? There's some, side effects, assignment statements, what have you. These two programs are surely not going to be equivalent. Okay, not valid in most programming languages. And indeed, for any particular source of randomness, these programs will indeed return different values for the sample. On the other hand, when we consider what happens when we integrate over all possible sources of randomness, right, the differences integrate out. So these programs are in fact equivalent. That's that's something that was at least very surprising and counterintuitive to me. Right. So the problem we tried to attack was, how do we show that this program is correct? Right. So this is a local transformation, but probably this transformation and all the transformations that we talked about are part of some larger system. So we need to know that our local transformations are valid in context. Okay. And that, of course, is the old problem of contextual equivalence. Two program fragments might behave identically in isolation, but we don't know necessarily whether they still behave identically when they are embedded in some larger context. And this is the kind of issue that a compiler needs to deal with when it is doing program transformations. All right. So to attack this problem, we need to specify what are the contexts, that is, say, what language are we talking about? And uniquely for this probabilistic setting, we need to be careful to understand what we mean by has the same behavior. All right. Same behavior is something that's kind of well understood in the functional realm, but maybe not so obvious in this realm. Okay, so we chose the most general language we could think of. A lambda calculus which is untyped, because we didn't want to make arbitrary decisions about a type system. It's going to be high order, because after all, we at Northeastern, we're schemers at heart. We allow unrestricted recursion. Okay. But the one thing that we're making a concession on is that our sample is going to be samples from the unit interval, because samples from other kinds of spaces are problematic. Oops. Back. There we go. So there's our language. As you see, it is a lambda calculus. It is higher order. It has application, that red V applied to V. It has our two effects, sample, which has the effect of sampling from a source of randomness, and factor, which has the effect of multiplying the weight of our current sample, or current run, by a value V. So variants of this language have been studied by a bunch of people with different design decisions for different reasons. So do they have continuous choice? Do they have scoring? Do they have recursion? Do they have non-termination? And the only language that actually has all four of those prior to ours is the one by Bergstrom and company in 2016. Unfortunately, they were not able to show commutativity. But our column is all green. Okay. Ta-da. We'll give ourselves the gold star. Though I should mention, by the way, that there was a very lovely paper by Kamar, Vakar, and Staten that I heard at Hope yesterday afternoon, which also is all green, using very, very different methods. And has recursive types, yes. But we have no types. You can do anything. Okay, so if we are going to give ourselves a gold star, one thing I should communicate to you here is what our secret sauce is, right? Which, of course, I've accidentally shown you the slide 3 times now. Okay, so our secret sauce has 3 main ingredients. We use tree-shaped inherited entropy. We use small step semantics, and we use step-indexed biorthogonal logical relations, okay, which is less complicated than it sounds. Okay, so first ingredient, your randomness as a finite sequence of random reals from 0, 1. Okay, because if I say, oh, my let expression computed V2, right, under some string of random numbers, well, what's the sigma 1 and what's the sigma 2? I don't know. Okay. Instead, we use a surjective pairing property. So inside every random real between 0 and 1, there are 2 more random reals. Take the odd-numbered bits and the even-numbered bits. Okay. And so if I have a let expression, you run it with some random real sigma, right? You run E1 with the even-numbered bits, run E2 with the odd-numbered bits. Okay, entropy is inherited, not synthesized. Okay, ingredient number 2, big step semantics is pretty. Small step semantics turns out to get you farther. We have an abstract machine with 5 components. This is not obvious. I got it wrong several times before we got a version that worked. How do you run this machine? Well, let's see. You choose starting values for each source of randomness, sigma and tau. We choose a target set A, a subset of the reals. We run the machine to completion. observe the final result R and the weight W. If R is in the target set, you accept this run, give it weight W, and throw it into your sum. Otherwise, throw it out. And now integrate over all the possible runs. If you look at all the possible runs, how often is the result in A? And this gives you a measure on the reals. For the whole program, the behavior is defined to be the measure with E and the continuation that just says halt. Okay, measures are non-normalized probabilities. Right, I said measure there. Measures are non-normalized probabilities. If you want to think about the relation between measures and probabilities, right, the measure for A is the area under that curve. So these things are closely linked. And two programs are equivalent if they have the same measure. Now we get the standard notion of contextual equivalence, but that's really hard to prove two programs are equivalent. So we use step-indexed biorthogonal logical relations. Okay, these work by induction on the length of the computation. Okay, and we throw on at the very end a soupçon of biorthogonality by doing relations on continuations as well. And now we cook it up. And what do we get? Well, we get the fundamental theorem that says that two expressions are contextually equivalent if and only if they are equivalent in the same continuation and the same target set for every continuation and target set. That turns out to be much easier to deal with. Okay, you get applications, right? So you get beta value, you get any mathematical equation, right? And now here's the interesting thing. Let's say you have a transformation on entropies such that if you run E in sigma and E prime in this transformed entropy phi of sigma, and it always is the same answer, then E and E prime are contextually equivalent. And that gives us our commutativity result. Okay, so here we have let x1 equal E1 and let x2 equal E2 and E0, right? If our first expression terminates, well, it will do so with under entropy, always going to look like the stuff we used for E1 composed with the stuff we used for E2 followed by other stuff. And then, well, the second one is going to give you the same answer in the entropy that we used to use for sigma 2, we used to use for E2, and then followed by the entropy we used for E1. Comes out the same. That phi is measure preserving, which is easy to show, and so we get the result we want. Okay, but wait, there's more, right? There's an equivalent big step semantics. We have a characterization of a very useful class of these measure preserving transformations. The fundamental theorem is verified in Coq, and so on and so forth. Okay, and I have 1 second left. Open questions. Can we apply these transformations to a practical compiler? Maybe. Don't know. Okay. We've gone from no semantic to multiple languages and semantics. How do these different systems compare? Do they validate the same equivalences? Okay? And Mike has not yet thrown me off the stage. Okay. And that is indeed the end. Thank you.
Thank you very much. So you just mentioned there are these other languages. So Jenny Hackett asks, how does your language differ from that of Borgstrom? Did you just happen to find the trick to proving commutativity, or does your language have some extra features to enable this?
There are a couple of extra features that turn out to be needed, a couple of extra primitives down at the bottom, but mostly the trick is the different treatment of entropy.
Thanks. Fritz Henglein asks, I can make sure I read this correctly. Commutativity seems natural when interpreting programs as operating monadically on distributions. Can your paper be understood as requirements on samplers to statistically correctly implementing such a denotational semantics? Are all samplers correct?
Well, first of all, I doubt that all samplers are correct.
Yeah, me too.
Just as a matter of principle. Yeah, I think that would not be unfair. There are characterizations of probability theory and randomness in which commutativity, they talk about commutative monads. Anders Koch has a model that takes that as a primitive requirement.
Okay. Well, one more, I think. Ejiro asks, could you give some interesting example in your language where the programs are equivalent in isolation but not so in a context?
I don't think such examples exist, based in part on Ohad's result that actually gives some denotational models for these things.
Okay. Thank you very much.
Thank you.
Okay.